All right, I would say we start. We were just reminded of scientists typically having back-to-back meetings and sometimes being a bit late, but I think that's fine. And I think we just start off. My name is Marina Andrijević. I'm based at IASA. It's a real pleasure for me today to moderate today's talk by Mark Dekker from the PBL, the Netherlands Environment Agency, and Utrecht University. As you might know, this webinar is happening in the context of Mark being awarded the Early Career Researcher Award at the last year's annual meeting of the IAMC. Congratulations again, Mark. He won this prize for his really fundamental and innovative contributions to advancing integrated assessment modeling, in particular through the development of new methods to disentangle uncertainty in climate policy scenarios, including fundamentally his work on understanding model fingerprints across scenario outcomes. Through the contributions that Mark made, it was highlighted in the speech at the award ceremony that his contributions enabled clearer interpretation of model behavior and more transparent communication of scenario outcomes, which is something that I think was very welcome in this community. Mark, I had a look at your publication list and some of the work you did before, including a very interdisciplinary portfolio of your PhD work. And it looks to me like you could have ended up optimizing railway systems or providing advice to diplomats or giving some insights even on how the human brain works. So I think the IAMC is really lucky to have you, that you've chosen to join this scientific community, because you could have easily gone in a different direction. And it seems to me as though you looked into the IAMs and wondered what's among the more difficult questions that are left to still tackle. And you decided to grapple with some of the fundamental methodological questions in the IAMs. So again, I think we're very lucky to have you. And without much further ado, I would hand over to you. I'm sure you have a lot to say. And I just want to say that Mark's talk will take around 40 minutes, but throughout the talk, we'll have a few opportunities for questions. So you can post your questions in the chat. I'll be keeping track of those. And then we'll have a couple of sort of natural breaks in Mark's talk where we could also address some of the questions in the meantime. And then again, of course, have a longer discussion at the end. So Mark, the floor is yours.
Thanks a lot, Marina, also for the kind words. And very happy to be here. Let me first share my screen. So here we are. Do you see it in the right mode? Yeah, perfect. I see you nodding.
Yeah, perfect.
Okay, yeah, because the nice thing of such a webinar is that you can kind of choose the topic. Of course, it must be related to the reward and stuff, but what I try to do here is to link a couple of the works that we have been doing and are currently doing together under one banner. You've all read the summary, I guess, otherwise you wouldn't be here. But the idea is that we today talk about large scenario ensembles and then specifically methods for dealing with them. And maybe as a subtitle, you could say, trying to unpeel the scenario ranges a little bit that are associated with these scenario ensembles. That's the idea. By means of an introduction, let's together have a look at this graph, which is from the AR6 database, all C1 to C3 scenarios, so those are the well below 2 degrees scenarios of primary energy oil over time. You would expect maybe for well below 2 degree scenarios that these scenarios have decreasing oil because fossils generate emissions, etc. But if you look at the 2040 values, well, there's actually a substantial portion of scenarios that have increases. And so even up to 40% increases towards 2040 compared to 2020. This is something that is, of course, relatively difficult to deal with in our communication, and something that today we would like to disentangle a little bit. And I think there are at least 3 ingredients that we should talk about, not necessarily meant to be comprehensive, but those would be the topics of today. The first one is about models, because of course part of this spread is due to, even if you would have a very tailored scenario protocol with maybe even one scenario description, different models would present different outcomes. This is one key thing that we will be talking about today. Another element is the degrees of freedom. It's related to model bias in a way, but also maybe a topic on its own, that if you have set a certain constraint, for example, a climate target, say you want to have, or a remaining carbon budget, for example, there are multiple degrees of freedom. There are multiple solutions or pathways that can end up with the same goal. And if you would look at only one variable, like here, oil, that may not be as noticeable, and you would maybe only stare in confusion to a spaghetti plot. But there are tools, and I will present some of them to deal with that, say, plurality of the solution space. You could also say it like that, maybe. Multiple lines and pathways reaching similar goals. And a third thing that I will be talking about is that we use in our community to describe, such spaghetti clouds, we use distributions or statistics from distributions a lot. But as I guess many of you know, there are things that need to be considered when doing so. Because is this a nice, well-shaped, well-varying distribution for your question? The answer is probably no, because this is the IARC database, is just a piling up together of various projects. And of course, it's a super important and a nice effort that we have such a database, but it's not the statistical sample that you may ideally want. So we need to talk about distributions as well. These three are the three topics that I will be talking about today. And after each of these topics, I will have a short break, and we can, or a Q&A point where we can ask questions that may have arisen. So that's the idea. Talking about model bias first. And I want to split that even up in two things. Let's first try to understand what are we even talking about? Where do models differ in? And after that, that's the important thing that you see on the slide. After that, try and see, okay, now we know what model differences are. How important are they for our work? And how does that differ for different variables, maybe? So that's the line. First, about model differences in general. So what are we talking about? I wanted to go to this figure first. This is maybe a bit of a complex figure, but if you look at it, not as complex as you may think. On the vertical, you have carbon intensity, so that's emissions per unit energy. On the horizontal, you have energy intensity, and so that's the energy consumption per unit GDP. And we all start, this is IARC database only for 3 models. We all start in the bottom right, because energy intensity and carbon intensity, because of efficiency gains, are always decreasing, or almost always decreasing in our scenarios. Why do I want to show this in light of model differences? Carbon intensity and energy intensity are, I think, some very fundamental properties of scenarios. It's not about individual technologies trading off. Are you going for solar or for wind? Based on the cost, maybe. Now it's really about, are you gaining part of your mitigation through the energy side and the consumption side, or through the decarbonization side? And even there already, if you look at the full IARC database, you see clear coloring in this of parts of this phase space by the different models. You see, for example, message over there having a relatively narrow bandwidth in this phase space, always, well, not always, but commonly following roughly the same trajectory or the same area in this phase space, distinct from image having always slightly more energy intensity reduction and therefore probably slightly less carbon intensity reduction. So already at this fundamental level of, well, the Kaya identity, for those that know it, you have these distinct differences between models. So that just to highlight how big this is. And you can, for example, here I have a 2050 snapshot. You can look at it in more detail here, where you have clear lines over here, which, for example, in brown, and message again, this bandwidth over here, just to, on this fundamental level, show how far they go. To deal with these model differences and to also map them a little, get an understanding, we created a little more than 2 years ago a framework that we call the model fingerprint framework. Building on previous work on diagnostics, we came up with approximately 20 diagnostic indicators. So those are indicators that say something general about the model output, about the model behavior, categorized in 5 dimensions. So here in green, you see the responsiveness dimension. Those are indicators about, for example, the sensitivity to carbon pricing or the maximum mitigation speed. In yellow, you see things about the mitigation strategy. So the carbon capture, dependence on non-CO2 abatement, but also CI and EI reduction. In blue, you see energy supply, which is a very simple indicator, a set of indicators, but of course very important. On the energy demand side, we focused on mostly electrification, but also hydrogen. And in purple, you have your indicators about costs and effort. So how costly does your model think that something is, some kind of policy? But also, given the same carbon pricing, how much does your model transform in terms of the primary energy mix compared to others? So this set of diagnostic indicators we compute not on a database like the AR6, because you have all kinds of different scenarios in there. No, what we did is create basically a laboratory experiment, which we call a diagnostic exercise or a set of diagnostic scenarios that are very stylized, that are very clearly bound. We ran it with 8 or 10 models, I believe. And then plot the results in respect to what is that inner circle, the ensemble median. So you get a little range for every of the models. And the result is this. You get pictures like this. So for every model, you have a bit of a range. And if you have an area towards the outer ring, that means that you're above median. And if it's towards the inner circle, towards the inner ring, or the center, basically, it means that you're, in terms of that diagnostic indicator, below median. And we call these the model fingerprints, basically. And you can have one per model version, basically. That's kind of the idea also for the future, but I will come to that. So let's look at a couple of examples. So here's image 3.3. And we run the scenarios, and R1 is about the relative abatement. So the overall sensitivity to carbon pricing, basically. And you see that depending on the scenario, it's roughly around the median. Okay, so that's one. Here's another example. I hope you can see my mouse, and otherwise I'll simply describe it in the blue. So ES123. You see that image is above the median. It's towards the outer ring. And that those energy supply indicators are about fossils. So it's a relatively high fossil heavy model, at least this version was. And then looking at energy demand over there, particularly ED3, energy demand indicator 3, you see that's very close to the center, and so way below median, which is about, and that indicator is about electricity in buildings. So that's an interesting one, right? So that means that if you read a paper where only image is being used, and that's about buildings, then it is important to be aware of the fact that typically image has much lower projections of overall electrification in the building sector with respect to other models. So it is also a way of not only teaching us as modelers, but also a way of, basically a side note to papers focusing on single models. And likewise, here you have remind, the relative abatement, so the overall sensitivity to pricing is higher, one of the highest, I would say, in the ensemble. And you also see that for these similar scenarios, fossils actually all below median. in blue. And then not focusing on ED3, but on ED1, which is about electricity in the transport sector. Remind goes, out of the scale even. It's more than 2 standard deviations higher than the average. All of them. So that's also very interesting to be aware of, that it has so much higher electrification in transport. Again, reflecting why it is important to be aware of model differences in general. Okay, so if you thought this was interesting research, then I have a message here for you, so a little commercial here. At the IAMC level, as part of the scientific working group on model diagnostics and evaluation, we are launching a pilot to do this actually not within one project as the paper was, but across the full community, so that everyone can submit these very simple stylized scenarios, carbon price driven typically. Yes, there are options for all kinds of more interesting scenarios, but the basis can be just a couple of very simple scenarios. And then we can try and set this up for many more models and have a much better comparison. And if we repeat that every so many times, every so many years, this, I think, will be a good way of, say, professionalizing diagnostics in our community. So please, if you're not part of it yet, please, head to either the QR code or contact me. And for those that are already involved, what we're working on now is the model registration part, which is now pending or very, very soon done. And then you can start submitting your scenarios. We want to show first results in Athens at the IAMC this year. Okay, so second part of model bias, and after that I can stop for a couple of questions. I first want to address the other part of model bias, namely not only understanding where the differences are and how they look, but also where are differences even important? Because sometimes you may look at a result and see, whoa, these model differences are very big, but you can still maybe sometimes say something robust about it. And this already gives a bit of a tension between what are absolute model differences and what are relative model differences. I hope you're still with me on this, and otherwise I'll explain it in a minute. So this is more about this absolute part. So this is, I think, a very interesting paper on the AR6 database, doing an experiment on what happens if you only focus on the most prevalent model in the database, or what happens if you remove that model. What happens to general statistics? So here in panel D, so to the right, you see a coal phase down in 2050 with respect to 2019 for, I think it's C1 scenarios, maybe C1 and C2 could be. Doesn't matter for the illustration. The median coal reduction is 95%. That's the black circle over there. If you remove Remind, which is the most prevalent model in the database, you get 83%. So that's a huge shift, of course. And you see also the statistic in blue over there of Remind itself being having a median of 99% coal reduction by 2050. So even in something as crucial as coal reduction, this model sensitivity on the ensemble level, because that's now what we're talking about when we talk about importance of model bias, it can be huge. But then circling back to this question of where are model differences in absolute terms high, and when are they also in relative terms high? When can you still say something robust even though you have model differences? We have a method for that to find that out per variable. And I want to illustrate it with a couple spaghetti plots. So again, more data here. So this is the AR6 database, CO2 emissions over time. And this is super trivial for anyone here in the room to know that, of course, these upper CO2 lines are associated with higher temperatures. If you would now stratify the whole thing by temperatures, like I did here, on 1.5 degree scenarios and 3 degree scenarios, there's no overlap between these distributions. In other words, climate target is an important discriminator of CO2 emissions. If you would do the same for two models, Remind and image, for example, that's different. That's much more overlapping. This is all trivial, but it's making a point. If we would now go to the fraction of solar power in the electricity mix, things are slightly different. So if you there look at two temperature targets, you would expect maybe the 1.5 degree to be much higher. It is definitely higher. The median is definitely higher, but you see a little bit more overlap, even a little bit in the interquartile ranges than we saw in CO2 emissions. And if you would compare that to the two models again, it seems like even the interquartile ranges of the two models are more separated than the climate. In other words, that's the point here, the CO2 emissions were more clearly defined or discriminated through climate targets, while the solar power fraction much less so, and maybe even more discriminated by different models. And this tension of and this concept of relative model importance is something we are capturing with Sobol's method of variance decomposition. And for those that don't know the method, you can forget the name. The only thing that we are basically doing is, if you look at a spaghetti plot, how much of the variation that you see is due to differences in climate targets. That's one angle. Differences in models. That's the other, and other scenario assumptions. And these three things should add up to 100% of explaining your spaghetti plot. And you get triangles like this. So the green dot is one variable for one particular year. And if it's close to the upper corner, that means that climate targets are are mostly robustly linked to the variation in your variable. But if it's to the lower left, it means that there's no consensus between models that this is the case. Model differences supersede other variations or drivers in your variable. And you get plots like this. We apply it here to the electricity sector. In orange, you see fossil use without CCS. The total you see in the large bulbs. And you see that the total is also more on the upper part of the graph, indicating that model differences play less of a role in these totals. Interestingly, you also see this for renewables in green and CCS in blue. Always the totals are less model prone, which makes sense, right? Because models may trade off individual fuels or technologies, but then maybe have the same total in their scenario. Total fossils or total renewables, etc. So, for example, this strong climate relation you see in these kind of plots. So here you have climate categories. This is this IPCC classification, where you have coal without CCS clearly having a signal across different climate targets. However, renewables have something similar, but then in models. And so, for example, here's hydropower and solar power clearly having differences across different model families, even for something like solar power. And maybe for hydropower you expect it because it's a relatively static technology. So the idea that it's dependent on natural resources. So maybe you don't expect it to be hugely different between C1 and C7 or low or high temperature targets. Well, maybe for solar power you would. But as I showed in the spaghetti plot just now, model differences are huge there. And even on the database as a whole, superseding the signal that you see across climate targets. And for CCS in blue, including also BECCS, you see that also the individual technologies are quite model prone. While there's also quite a strong signal or relatively strong compared to other things, on other scenario assumptions, especially in the short run, which also makes sense. We often in our scenarios make scenarios specifically on CCS or specifically exploring that with the same model and the same climate target not being the major predictor there. And you can generalize this. This was electricity sector. You can do this also for emissions, where you see many emission variables, all in purple here, being mostly dominated by climate targets. So we have a robust link with that. But model-prone variables are clearly found for in the individual fuels that are not fossils. For example, the electricity in all the demand sectors, but many demand sector variables in general, actually. So also when you look at liquids and biomass in industry, for example, it's all very model prone, or at least the variation that you see, that signal is mostly due to different models showing different things rather than different climate targets showing different things. Yeah. Okay. So I talked a lot about models and how they play a role in these large ranges that we see. I want to pause here a little bit. Maybe there are questions on this, and then after that I can continue with the next part. Maybe Marina, you can.
Exactly. I don't see any questions in chat, but there's a hand up by Yanbu. Please.
Hi, Mark.
Perfect.
Nice. Yeah,
Hi.
of course. Yeah, really great talk here. Yeah, so in general, yeah, definitely I read your paper and understand there are some like model-driven bias, but did you ever do one step further, like why some models prefer something? Is that because some techno-economic assumptions or the model solution algorithm or something regional resolution, whatever? So any one step further?
Yeah. It's a very good question. And it's a question that also has a bit of history also in papers on diagnostics. So Matthijs Harmsen wrote a paper in ERL in 2021, also on diagnostics. We basically build on that. He's also involved, by the way. But already there, they started asking that question. And both there, as well as during our writing of the model fingerprint paper, we couldn't easily find such a relation. So we made plots like, process-based or iterative models versus optimization models, and these kind of categories you then try to relate to certain biases or certain fingerprints. But I think, but we couldn't find it, and I think this is partly because we only have so many models. Yeah, so maybe 10 with sufficient representation across all climate targets, because that's important for such analyses. And even within that small population, you have so much diversity. And so it doesn't only boil down to something very structural as being optimization focused or being iterative / process based. Those relations we can find, and we realized that there are so many ways models can vary that it is difficult to pinpoint it directly. Of course, I guess the way to go there, if you would like to answer your question for a particular topic, would be to then, as I said, specify the topic and dive there into how it is modeled in a particular model. But overarching statements like, for example, the relative sensitivity of Remind to carbon pricing, the low fossils, and everything that's connected to that, and how the electrification on the transport sector is related to that, I don't think there's a single answer to that.
Yeah, just quick comments. Like we were doing some like multi-version model comparison, just the same class of GChem, different versions, so we can really isolate the specific feature. And we were doing something really interesting, and happy to chat with you later.
Yeah, let's do that. Well, we have something planned anyway. But yeah, and good to mention, by the way, is I was making this little commercial about the diagnostics exercise. Right? The idea there is that we do this also by model version. So not only by by model, but also allowing modelers to submit these scenarios for multiple model versions, or maybe in a year later, if you have a new iteration of your model, submit it again, so that you can compare your delta. So that's for yourself, that's very teaching. However, I'm not sure whether it automatically leads to the larger question that you're asking, Jan, on how model fingerprints compare to other model families are where the roots are for that. That's a very complex question and may differ per topic, I guess.
Thanks, Jan. I see Brian O'Neill's got his hand up too, but if that's okay, Brian, if we could maybe come back to your question later in the interest of time, perhaps would be better to move on because we're 30 minutes in. Mark, also for your orientation, if that's okay.
Yeah.
With you, Brian.
Yeah, sure.
But please remember it.
Yeah. Definitely remember the final part about distribution is very short, so I think we'll manage in time. So let's come back to it. About the degrees of freedom. So this is partially related to model bias, right? It's a complementary topic, not totally different, but it's just another lens to look at the spaghetti plots that we saw earlier. I remember that this is oil for well below 2 degrees scenarios. We have oil rising for these ambitious climate scenarios in 2040. An expert, I'm not an oil expert, but I guess one of you definitely is, would definitely say, when you're high in oil there in 2040, there are certain conditions to this. For example, other fossils are maybe very low because only then you can meet that well below 2 degrees. I mean, the climate policy needs to land somewhere in your system, right? Or maybe you are reducing non-CO2 emissions very rapidly. These kind of elements should be part of that upper range. And at the lower range, same, in the sense that even though we know that that's saving a lot of emissions, that has major consequences for your transport sector, for example. Probably a lot is electrified, or the demand is not rising as much as in many other scenarios. So these kind of elements, these kind of conditions are very important to interpret these spaghetti plots, these ranges. So only looking at ranges with, I don't know, this gray area without linking these individual lines to other conditions is prone to misuse. I guess an oil company would take the upper limit here, without necessarily considering what that does with other elements of the system. In other words, the red lines here have their own conditions separate from the blue lines, basically what I already was talking about. But you need to have a bit of a multi-dimensional view on this. And I want to illustrate this with this plot. Because the purely looking at oil doesn't give you the information you need to really contextualize the red lines versus the blue lines. Multi-dimensions, of course, helps with that. So here we have final energy on the vertical with renewables on the horizontal, and again, well below 2 degrees scenarios. And again, here you may ask, okay, these are ambitious climate scenarios, but still we have this huge range for primary energy renewables, right? Going from 150 exajoules to, this is 2050, I think, 150 exajoules to 1200. So there's a huge range. But adding final energy to it helps us to start looking a little deeper in this data, because the overall relation between renewables and final energy is maybe quickly made. And you can have low renewables in your ambitious climate scenario if maybe overall final energy is also low. So then it makes sense that you don't need as much renewable energy as you may expect in an ambitious climate scenario. And likewise on the high side, right? So this relation, this scaling, we understand. And with this 2D picture, we also see the yellow blob over here, where we have maybe counterintuitively for these ambitious climate scenarios, low renewables, but high final energy, leading to maybe scenarios that are associated with relatively high alternatives, CCS, nuclear, you name it. And this idea of going into higher dimension is something we are currently generalizing. So coming plots are all, say, new research in prep. soon to be submitted. What we did is we took the Scenario Compass Initiative, a database, and looked at all scenarios well below 2 degrees. And from that set, looked at the fossil projections separately from the mitigation strategy projections. Mitigation strategy, by that I mean all other variables that are relevant to your mitigation strategy, but not fossils. So things like final energy, renewables, CCS, CDR, electrification, these kind of variables. And we needed to, for this method to work, to have full complete reporting. So that's why the numbers, which is the number of scenarios, you see decreasing. And what we then did is we did not think about the 2D picture that we just saw. We did not specify that space ourselves because variables may be correlated, because maybe some things that we think are very important actually do not really matter to differentiate scenarios. No, what we did is we trained a deep learning algorithm called a variational autoencoder, for people that know it. That basically, there's an analogy with PCA here, principal component analysis, for those that do know that basically tries to condense all the patterns and relations, also over time, that is in the data into a very small condensed space. And because it has to do this with these two big neural networks, it only finds the most important patterns that differentiate scenarios. Because based on that information, it can then decode in turn into a reconstructed output. That is how a VAE of a variational autoencoder typically works. But this talk is all about that Z over there is the latent space. So that's this very condensed space where all these pattern information is embedded. And what we then do is on that space do a clustering algorithm. So that you basically on the important dimensions get clusters or groups of scenarios that tell a similar story, like the yellow part that we saw in the previous plot. And we call them typologies because these groups all have a typology, a certain narrative, a certain peculiarity that makes them different from the others. And we explicitly do this on the fossil side. So we have fossil typologies, and on the mitigation strategy side. Because sometimes you can have different fossil pathways, fossil projections, with a similar a thing that happens in other elements of your energy transition. And vice versa. You can have with one, for example, all fossils going down, you can do that with different mitigation options. And so there's no bijection between the two. You get typologies like this. So this is an example. Overall phase down is what we have come to call it. 120 scenarios that all show across all three fossils, so it is coal, oil, and gas, lower than median values. That is arched in the green part. The dashed line is the full ensemble median. So all fossils go down. That's a very simple group of scenarios. 120 are showing that. A different one is that it found 60 scenarios that all have the peculiar aspect of coal being revived. So that is that's relatively unique to this particular topology. And you see much higher coal use across the century, but especially this revival thing is an interesting element of that one. And this way, we found a total of 8 of such fossil typologies, groups of scenarios that have similar trajectories of fossils. And we did also do this on the mitigation side. I'm not showing all the results in light of time. And then the interesting part, maybe just to highlight a few, you see typologies focusing on delay. Also, the temporal element is very important. Here, stagnation also, so overall degrees of fossils. And this revival element is also very interesting. It's usually associated with huge amounts of CCS, just as a FYI. And then we relate those fossil topologies to the strategy topologies, so to the mitigation side, and see where they overlap and where don't. And you see structure. I'm not going into all the details here. And typically, of course, the high fossil topologies associated with high CCS and CDR. But sometimes there is an interesting other combination possible. But you do see clear structure between it. Now, and our next step in the work was to not only present the topologies, but also qualify them. And I think this is a very important step in order to interpret, do I even want to be on this upper range of the oil? Remember this plus 40% in the spaghetti plot I started with? Do I want to be in that upper range? Well, that is what this is about. Across a couple of dimensions, building also on some work from Hamish Beath et al., and also the Scenario Compass Initiative vetting, we create plots like this, again, not going into all the details, but across all the typologies, for both fossils, as you can see on the to the left, fossils and the mitigation strategies, we evaluate, are there concerns regarding historical vetting, regarding model diversity, regarding economic feasibility, or even interregional fairness, sustainability, such kind of things. And then you see some structure popping up with typologies with high fossils and high CCS, having concerns regarding feasibility of CCS and CDR, having concerns regarding interregional fairness, but also this, for example, this high revival of coal is a very peculiar one, but that's also clearly something. Now, not specifically that one, but some of the fossil topologies have clear model diversity issues because they have a clear, model fingerprint. Basically, the algorithm grouped only, remind models, remind scenarios together. So all these kind of things are important to start interpreting these topologies. So that's what I wanted to say about the degrees of freedom. The point of these spaghettis having all kinds of different scenarios that can reach a similar target, which you can maybe best study, or study at least well, by grouping scenarios together that have a similar story, so that all these disclaimers of all parts of the oil range, so to say, are being clearly mapped. That's what I wanted to say about the second thing, Marina.
Thanks. Great. So if Brian's question is still relevant now, maybe he could ask it now. Otherwise, again, fine to save for later. Anyone?
Yeah, my question goes back
Please, Brian.
Mainly to model bias, so it's probably better to wait.
Okay, sure. Okay, if there are no other burning questions, Mark, perhaps you carry on.
Okay, fine. So the final part, distributions, is much shorter, and also a bit maybe speculative even. So the point I want to address, because it couldn't miss in a presentation like this, that with these spaghetti plots, again, I already indicated, the database is just a grouping together of scenarios from all kinds of projects. A great effort, very important, but it's not a statistical, nicely varied ensemble. It's not a Monte Carlo situation where you know what you varied and all in a maybe a nice sampling method behind it, etc. So there are problems with the distributions there, partly because of model bias, maybe also project bias, maybe also topic bias, certain types of explorations of the future being underrepresented. So that is definitely something that we need to work on, or at least something need to be aware of. And one effort on this I want to mention in this context, which is a recent paper of Hamish Beath et al. I was honored to be part of it, is a framework where they also posed this question, basically, and identified at least 3 things what you need to consider when using distributions from these databases. The relevance of the scenarios that are in there to your question, the quality, to what extent, maybe even epistemologically, the quality of those scenarios to your question, and the diversity of the scenarios in relation to your question. And let's zoom in specifically on the latter part. Diversity sounds maybe a bit vague, but you can imagine the situation that if you have a database where you have, 10 different scenarios. Okay, very small, 1,000 scenarios. But then you resubmit one particular scenario 1,000 extra times. Then, of course, that biases all distributions and all plots that you will make. That's because there are duplicates in there. So somehow you want to take into account or redistribute your distributions such that it tries to prevent this. And that's what diversity is about. It tries to weight scenarios. These 1,000 extra scenarios would be downweighted based on how close they are or how similar they are to other scenarios that are already in there. And you get plots like this in the paper. So focus on panel A here. This is net zero GHG. For every climate category on the horizontal, you have an unweighted on the left and a reweighted version on the right. And the red dots that I added here are shifts of the median due to this process. And of course, some care must be taken here. This is a kind of a gray or exploratory area because you don't want to downweight consensus. If a lot of scenarios say the same thing, that could also have a reason. So there's a gray area here, and I think we need to, as a community, work on this further to ensure if we need to work with distributions, and there are, I think, a lot of situations where we shouldn't, and maybe work with typologies or example scenarios, etc. But if we really need to work with large ensembles in one figure, then be aware of the distribution implications that your method has. And again, returning to this, I think, beautiful waterfall that we see here, you could look at it and also wonder, why doesn't it cover the full space? There are, of course, really physical reasons for this, but is it covering the full space that that is maybe possible in the future? And this is, of course, the never-ending question we have in our community: are we exploring all possible futures sufficiently, or are there maybe also gaps in the data that also affect the distributions that we're working? And so, for example, if you look at this graph, which is this 2050 snapshot of the waterfall graph that you saw just before, you see a certain bandwidth in 2050. Is there a real strong physical reason for that? Probably yes, but how strict is that, and what kind of things are driving that? And efforts like for example, introducing strongly interregional and deviating emission targets compared to our typical globally cost optimal runs. Where in this figure are they? And does that implicate that maybe there is a whole range still to be found? These kind of questions, I think, would be super nice. Bit of the frontier maybe of our field as well. So if you have thoughts on that, let's definitely talk about that. Okay. Those were the things that I wanted to mention. I have 3 final remarks, and then I'm done. 3 take-home messages, which are a bit maybe own opinions as well. For the community, basically. This is the community talk, right? So one thing that I want to re-emphasize, I was talking about it, but I want to re-emphasize it again, is that we maybe somehow could think of making a diagnostics a standard practice in our projects. So we have a lot of projects on a particular topic, afforestation, for example, and we do model development and we do our MIPS. And those MIPS end up in the database. But I think it would be super nice if we come to a practice where, we did model development, and directly after that run a couple of super simple scenarios, diagnostic scenarios, that are standard and we have run before and are in this diagnostics database. And we can recreate these fingerprints and really see the delta because of our new afforestation developments. I think that mode of work would be super nice for our community. And again, I have the QR code here for the invitation of this pilot that wants to work on that. Second remark, let's explore emulators. Because a lot of the topics that I was talking about earlier, things like input-output relations, the sensitivity to things, model bias also. That's, for example, what you see in this plot, a nice paper by Lee et al. In Nature Climate Change last year. Panel C here, you see the feature importance as proven by their emulator, or at least their deep learning algorithm shifting when you remove different models. So that studying that can also be done with emulators. Irregularities in the database, something that is sometimes difficult or noisy to work with if you work a lot with the database, can be partially helped using IAM emulators. So I think there's a lot of potential there, and of course a gray area on what do they learn and what not, but something to explore. And a third thing that I want to say is reiterating, avoid using full ensemble statistics where possible, because if you do not have stratification, and even if you do, but only on the climate level, we have seen that both a model dependency can supersede signals, but also it can be facilitating misuse. And working with, for example, as IPCC did with IMPs would be very nice. Single cherry-picked scenarios to show some illustration. But of course, that is then in turn prone to outlier picking. Or typologies, which has a more subtle signal. For example, if you want to have a low demand typology, the group will also always have a less strong low demand than if you would pick a single one. But it would be more representative or more robust. So that's the third message that I want to pose. And that's it. Thanks a lot.
Thank you so much, Mark. Great talk. Lots of virtual clapping going on. Mm-hmm. Let's use the last couple of minutes for questions. I think Brian could go first, but please, so everyone else.
Yeah, thanks, Marina and Mark. That was really, really fascinating talk. So lots of stuff I could ask or would be great to discuss more. But what I wanted to raise about model bias is maybe, a little bit more surface kind of thing, but it's sort of in the direction of Yang's question and kind of both what we do with it, but also how we characterize it. I think that, right, because fundamentally it's a positive feature. It's the point of having these multi-model ensembles in the first place. If you didn't have model bias, there'd be no benefit to a multi-model ensemble, right? And this is something that we try to take advantage of. Climate models try to take advantage of, and so on. And so I wonder, for one, is it just simply a communication problem of even calling it model bias, right? The word bias is like, those IAMs are biased, and right, nobody knows. You get one answer from one and one answer from another, right? That's a problem, right? That's a problem for IAMs already. And so I'm like, I totally agree with your three takeaways and all of the work you did here, but I wonder if there's a way to just recast this a bit to I don't know what to call it, but to present it that way, right? As this is something we want to take advantage of, but do it right.
Yeah, great question. And fully aware of this. And honestly, also when I use the word bias, I'm also not using it in a negative sense. Bias just as an objective thing, namely that there is a shift in tendency or shift in behavior compared to not having that model, for example. So yeah, I fully agree. And maybe you're right that there's a communication aspect to it as well, because bias sounds negative, and maybe we shouldn't use it like that. I think that model differences could have multiple causes than only this degrees of freedom thing. And because that's, I think, what you're referring to, that different models can shed different ways to the same goal, or different pathways from the same scenario assumptions. So in principle, my 2 chapters on model bias or differences and degrees of freedom would be connected that way. That is one cause of model differences, but of course, there are also other causes related to differences in input data, parametric differences, and these kind of things. So some of them indeed provides us new knowledge of mitigation solutions, and some of the things are because of other uncertainties, some models having a more refined modeling of a particular sector, etc. So to really call it a one-to-one relation between what are model differences, well, they're simply different versions of the future. I think more research is needed to really extract what is now the part of the different futures and what is the part of forms of uncertainty, some models being better than others in particular sectors, etc. So I would welcome research in that direction very much. Yeah.
And I realize you're using bias, right? It's a technical term, it's objective. I just think for other people, it's not, right? They're not aware of that. And so going further into like what is actual structural uncertainty? Is it parameter uncertainty? Is it, you mentioned also at one point project uncertainty, right? So you may have a bias in how much whatever wind energy a model uses because that model happened to do a bunch of projects on wind energy, right? And so also something worth distinguishing.
Yeah, I fully agree. Yeah. Thanks a lot.
Thanks both. Any other hands up? Maybe I'd ask a question, Mark, in this, also continuing in this, in the spirit of this discussion. When looking at the structural model differences, have you identified also things that could be simple fixes, quote unquote? So something that could be resolved with some sort of standardization or a convention, or when you show the graph on the translation between primary to final energy, I did wonder, and I know the IAMC has a sort of a reporting standard, right? But I did wonder if we are 100% sure that all models follow this, or if there could be some things that we could easily fix, not sort of recognizing that there are a lot more other things that require more analysis and understanding.
Yeah, good question. Also very difficult to have a single answer on. We didn't come across one particular thing to change. That's the short answer. The long answer is that I think these fingerprints are the start for reflection of modeling teams themselves. For us as Image, it was a start of being very aware of our fossil dependency, actually, and relatively high CCS, which actually in version 3.4 of Image is quite different now. So I do not have an explicit example or answer for what to change community-wide, but I think this process of doing diagnostics can reflect, or can help modeling teams reflect on these things themselves. And at the same time, and that's also in line with Brian's comment or question, what you don't want is that deviation in this circular diagram is seen as something negative. It's just good to be aware of it when you interpret a paper based on that particular model. It would be a negative thing if that paper was presented as a universal thing. No, it's an outcome of that model that has this particular outlook on the future. And yes, for some variables, as we have seen in the triangle thing, for some variables that matters, for others not. But yeah, in principle, this reflection element, I think something that I would definitely recommend rather than one fix. Yeah.
Thanks. And maybe also to highlight what I took as a substantive takeaway from this as well is that the models actually agree on the fact that we do need to phase out fossil fuels. So this is one area on the plot you showed that they all agree on. How we get there might be a more complex question, but this is also how it is. So I do think that we can also learn something sort of very clear that all models show. I'll let you give any final remarks, but from my end, thank you for the great audience turnout, for the questions, and I hope you keep up with the great work, Mark.
Yeah, thanks. Thanks all for listening, and great that yeah, also via this award, methods-oriented work is having some attention. I think that's a critical thing, and also quite an exciting topic to be working on in this age with emulators and whatever possibilities coming up. So for anyone that saw something interesting and wants to chat about it further, you're very welcome to email me. Thanks a lot.
Thanks all, and have a great rest of the day. And bye-bye.